Hi, this is Jacques Langloff. I'm professor at University of Strasbourg, France. In this short video, you will learn how to set up RPIt. RPIt means Raspberry Pi Target. It is a free Simulink coder toolbox that runs on Raspbian, which is the main operating system for Raspberry Pis. RPIt is not limited to the Raspberry Pi. You can also run it on an Intel platform and even run it on Ubuntu operating system, since Ubuntu is based on Debian. Let me first explain you how to install RPIt. So type RPIt into Google search bar. The first result should be the right one. So you have a French version of this page, but also an English page. And on this page, which is pretty long, you have some basic explanations about RPIt. So I will go through the main subsection of this page. And first of all, this figure that explains how it works. So you describe your system with blocks into Simulink. It is pretty easy to describe and to modify. And the Simulink coder toolbox converts this block diagram into C code automatically. And this C code is downloaded to a target and compiled on the target. This is specific to RPIt. There is no cross compilation, so the code is sent to the target, and it is the target that makes the compilation. It is possible on the Raspberry Pi. It has enough power to compile such code without waiting too long. Then automatically it runs the equivalent software of this block diagram. It runs it in real time on the target. So real time is in fact soft real time. So you can expect jitters around 50 microseconds. So 50 microseconds is pretty good for most applications. And at last, when the software, the code equivalent to this system runs on the target, there is a connection, a TCP/IP connection that is initiated between Simulink and the target, and it is bidirectional. So you can send new parameters, for example, for your blocks. And also you can have some visualization, in real time. So you can plug some oscilloscopes, virtual oscilloscopes, into your model, and you can have the signal displayed in real time into Simulink. So what's the main difference between RPIt and Matlab toolsets for example, for the Raspberry Pi or for the LEGO EV3? In fact, we optimized our toolset to achieve better response time. So you can expect to attain higher sampling frequencies with RPIt with respect to Matlab's toolsets. For example, if you use our modified firmware for the LEGO EV3, you can achieve 500 Hz sampling frequency to control the motor, for example. The communication here, the USB communication round trip between the target and the device is around 1 millisecond. So you send the motor control signals here, and you will receive back encoder's measurements in less than 1 millisecond. So on this page, you also have a list of supported devices. This list is not complete. You can add, there is a recent addition. You can now control dynamic cell actuators with RPIt. And here are the other devices. You can control an EV3 Lego brick, an NXT brick. You can use various types of IMUs connected to the Raspberry Pi. Even you can acquire the measurement provided by a Polaris system. A Polaris system is a 3D localizer. So this list will grow in the future. We add on a regular basis new blocks to our block set. Recently, we added, for example, a socket block that allows to communicate through socket with another PC. For example, we use this to make visual servoing. So you have a PC running time-consuming image processing. This PC is connected to camera, which was in this example a high-speed camera running at 500 Hertz, and so you can poll through the socket this PC to ask for the new values of, for example, some feature in the image, and you can use it as a visual feedback for visual servoing. Here you have some typical examples of how to use RPIt. So this Linux PC running Ubuntu and also running Matlab 2014A, and you can see here a Lego EV3 brick directly connected to this PC. So the target here and the platform running Matlab Simulink is the same. It is the basic configuration for RPIt. So you send the code on the same PC, which is also running the GUI, so the Matlab Simulink, and for practical session, it is particularly convenient. Here it is EV3 block brick. Here the NXT brick. And here you have a setup that is fully wireless. In fact, there is no connection here between the target. Here the target is a Raspberry Pi. The device is a Lego EV3 block. There is a connection, an USB connection between the Raspberry Pi and the EV3. And the EV3 is powering the Raspberry Pi thanks to the secondary USB port. It provides enough power to for a Raspberry Pi, a Type 1 Raspberry Pi. So we measured that this port is able to provide more than 800 milliamperes. So this setup is communicating through wireless. Here you have a wireless dongle connected to the PC running Matlab Simulink, and you have another dongle here in fact connected to the Raspberry Pi, and the TCP/IP connection is between this dongle and this dongle. So you can here mount this system on a mobile robot, for example, and have you can have this way a fully autonomous wireless system. Some words about performance. So I told you that RPIt was optimized for high frequencies, short delays. So for example, the communication with I2C devices like IMUs from Pololu or Drotec or Sparkfun. This communication runs at 400 kilohertz, and if you want to read all the values of the IMUs, so the gyro, accelerometers, and magnetometers, so 9 values, this needs about 1 millisecond. The communication with a LEGO brick, an EV3 brick, with the original firmware, it's also possible to use it in RPIt with the original firmware. You have a latency of 5 milliseconds, so max frequency of 200 Hertz. If you use the modified version of the firmware of the LEGO EV3 firmware, you can run at theoretically 1 kilohertz, but if you take a safety margin, you can achieve 500 Hertz. If you use NXT, there is a round trip delay, communication delay of 2 milliseconds between the target and the device, so you can achieve 400 Hertz or less sampling frequency. Let me show you now how to install RPIt, and first of all how to download it. So you go to the top of the page, and here's the link to the GitHub of RPIt. The newest versions of RPIt are now available on GitHub. So you click on it, and here you have the latest release of RPIt. You download the source code. It is a zip file. Okay. The size is about 25 megabytes. Very important, you have to, when you open the archive, you have to rename it. Sorry, you have to rename it simply RPIt in lowercase. And you simply drag this folder into your Matlab home folder. Here it is. So you downloaded RPIt, you renamed the directory, you put it in the root Matlab folder here, and now you can start Matlab Simulink. Here I have the latest release. It is a 2016B release. You go into the RPIt folder, and here you have a file, a script in fact, called setup. Every time you change Matlab version, or if you change the target, you must rerun this setup. You can rerun it as many times as you like. There are no harmful effects. In fact, if something is already configured, it will only ignore the configuration. To configure RPIt, you need a target. The target is auto-configured with setup. And here in this example, we have a very specific target. In fact, it is a Debian Linux system running into Parallels. Parallels is a a virtualization software running on Mac OS X, and I have here a virtual machine, Debian virtual machine running, and we need to know the IP address of this machine in order to do the setup. The IP address into the same subnet of Mac OS X is this one. I just have to copy it, and I will use it into the setup procedure. So I launch a setup. You have here some explanations on various issues that you could encounter, and also how to create an account, a Pi account, on a machine that is not a Raspberry Pi. For example, this machine has a Pi account. I created a Pi account, and this Pi account, it is very important, should have the same behavior than on a Raspberry Pi. For example, if I type sudo brush, there is no password. This is exactly the same behavior on a Raspberry Pi. And to do this, you only have to issue this command. Okay. So I continue with the setup. First of all, the setup compiles some MEX files. So you need, if you are running Simulink on Mac OS X, you need to have Xcode installed. So at the end of this compilation, it asks you for the IP address of the target. We just copied it, so it is this one. It asks only two times for the password of the Pi account. 1, 2, and after that you won't need anymore to type your passwords. The setup system initialized a passwordless SSH communication. It creates a private key, a public key. It uploads the public key onto the target, so there is no need for future connection to type in the password. So here the configuration successfully ended. And you can see that it also uploaded some files needed for the compilation of automatically generated code from Simulink. This is why you need to rerun the setup if you change the version of Matlab Simulink, because these files will change. And it also installs some packages needed for the procedure. For example, the screen utilities. This is a very common utility to run some session into a detachable terminal. Also, you need a libUSB to communicate with Lego bricks. And you need some basic configuration to access USB ports as user. So RPIt is now installed. We can run our first demo. Here in the RPIt folder, you have one subfolder called demos. You open it. You have many demos available here, and one is called jitter. You go into this folder, and there is one file called jitter.mdl. This is the Simulink description of this model. You double click on it. I already did it, and you should have such very basic Simulink block diagram. In fact, here you compare the time on the target. This block acquires the time by reading a hardware clock directly on the target. And you compare this value, this time, with the time given by the block digital clock, which is the time on the host, so the time on the machine running Simulink. This is a discrete time system, so you have to specify the sampling interval here, 10 milliseconds, so it will run at 100 Hertz. So 100 times per second, it will compare the time on the target with the time on the host. It should be the same. So if there is a difference here, the difference is the jitter. So we will have an ID, a picture on the accuracy of the real-time capabilities of the target. Here we are running a virtual target, so the jitter will be pretty high. But on a real target, on a real hardware target, you can expect with current version of the kernels jitters around 50 microseconds. So before starting this model, I have to configure it. So you click on the menu Simulation, you open Model Configuration Parameters. And here you have some subsection. In the subsection code generation, you click on interface, and here you have makefile arguments. Here you should put the IP address of your target. Very important in order to be able to communicate with it. It is the only configuration that you should do at this stage for this demo. So you click OK here, and now you can push on the button called Build Model. So this will launch an automatic procedure that will convert this block diagram into C code, that will upload the C code to the target, so here the virtual Debian, that will compile automatically the code on the virtual machine, the target, that will launch the resulting executable, that will connect Simulink to this real-time code through TCP/IP, and at the end you will have real-time data coming into the scope. So I click on this. So it takes a little bit time. Okay, you can use diagnostics here. You can see code generation step. Then target is not a Raspberry Pi, indeed. Compiling on the target, you can see here there is no error, no warning. The executable is compiled, it started, and the simulation, or it is not really a simulation, since you have some real target into the loop, is running. Here you can see that the time is increasing, in real time, and you can double click on the scope to open the real-time measurement of the jitter. Okay, so it is out of range, so you only have to click here. So there is some steps. This is normal. You may have some drift of the clock, the Simulink clock, with respect to the VirtualBox Parallels clock. But here you have an idea of the jitter. So you could have a good idea if I stop now this system. So to stop it, you only have to push this stop button. Now you can expand your result. If you zoom in here, for example, this portion of the measurement, you have here a variation of the time between approximately 398 here and 406, so 8 milliseconds jitter. This is a very huge jitter because we are in a virtual machine. But again, if you do this exactly the same on a Raspberry Pi, for example, you will have around less than 100 microseconds. And also you will not have these steps, this drift of the two clocks, which is due to the fact that here the target is running in parallels. In this tutorial, we learned how to install RPIt, how to configure it. We started our first model, which is a very simple block diagram that measures the jitter. In coming videos, we will go through more advanced topics. We will create some advanced demos using real devices like Lego actuators or IMUs or dynamic cells actuators. And we will also learn how to debug RPIt, because sometimes there is some communications problem between the target and devices due to wiring or user rights or other. And one complaint about RPIt is that there is very few feedback to the user on the Simulink side. And you will learn how to debug, how to access to more low-level messages directly on the target. So thanks for watching.